Well, we have more to say on surfaces today. Here's a fun surface that people know about called a Klein bottle, K-L-E-I-N. This is a one-sided closed surface, like the Mobius strip was a one-sided, not closed surface. This one, if you look at it, it has to pass through itself in order to make this surface, but it comes through here, and it comes back out like that, and there's only one side to this. These are surfaces we can't talk about in the following. We want to calculate an important quantity called the flux through a surface. And I'll just remind you, when we had a surface like this, here's some surface sigma, say, and it's being swept out by this position vector r of x, y, z, and x, y, and z are given parametric functions of u and v. And so if I have some point on the surface, it's got coordinates x of u0, v0, y of u0, v0, z of u0, v0, given by this position vector that goes out to that point. Now, at that point, if we consider holding, say, v0 fixed, v0 fixed makes r a function of one parameter, and it makes it a curve. And along that curve, where v0 is fixed and we just let u vary, dr du, you recall, for a curve given as a function of one parameter, this is the tangent vector. It points tangent to this curve in the direction of increasing u. Similarly, if we hold u fixed at u0 and let v vary, then we get a curve like this coming through here, and dr dv points tangent to that curve. And now, if you take dr du cross dr dv, you get a vector that's perpendicular to both these tangent vectors. You get a normal to the surface. We could call it n. Not a unit tangent in general. We take this and divide it by its length to get a unit tangent, little n, they call it in the book. Alright, so that was how we could find a normal to a surface. Provided it's an orientable surface, then we can have a whole, at each point, a normal vector to the surface, similarly to this one. Now, given that, we might be interested in computing the following quantity. Uh-oh. Where's my page one? It's underneath. There it is. Called the flux. Given an orientable surface, so we can have a unit normal, capital N divided by its length, we can take the double integral of f, the vector field, dot the unit normal of the surface ds. Why would that be an important quantity? Well, here's your surface again, and you've got a unit normal n. And if you look at what it's computing, here's f, the flow field. Suppose f is the velocity field of the fluid flowing through this surface. Now, if you take f coming at an angle to the unit normal n, then f dot n is what? It's this little length right here, because it's length of f, length of n, cosine the angle between them by the dot product theorem. But n is a unit normal, so this is length of f cosine theta. It's the projection of f onto this unit normal here, right? If this is f and this is theta, the angle between the two vectors, then this side of the triangle is f times length of f times cosine theta. So what you're doing is you're saying how much of the fluid is flowing out through the surface at this point, and if you integrate that over the whole surface, you get the fluid volume passing through the surface sigma in 1 unit of time. That's the significance of the flux. Let's move this down a little bit. How can we calculate it? There's this wonderful theorem. This is the big theorem for today. There's actually two. The big one is the one that follows from this one. It's a corollary, we call it. A corollary is just another name for a theorem. If you think your theorem follows quickly from another big theorem, then you can call it a corollary. And for us, the corollary is going to be more important than the first theorem. But suppose you have a smooth surface sigma generated by this position vector r of u and v through x, y, and z over a region r in the uv plane. And f is continuous with n computed as the RDU cross the RDV, the normal, divided by its length, so you get a unit normal, called positive orientation if you take the normal that way. Then the flux flowing out through, in the direction of the normals through the surface, is F dot dRdu cross dRdV dA. How can we prove that? Here's, I've called it reason. This is the flux integral we want to calculate. That tells you the volume of fluid flowing out per unit time through the surface. And you say integral F dot n ds by our theorem last time is F dot n times the length of dRdu cross dRdV dA, where A is the region R is the region of projection into the UV space. Well, we just said that n is the RDU cross the RDV over its length, so we put in what n is, and then these two cancel, and out pops the theorem, right? There it is. So, this is just a short proof, and now we've got another short proof. If you have a particular surface where you write z as a function of x and y, then you're identifying x equals u and y equals v in this theorem, and that's all there is to get this theorem, right? Because now, dRdu cross dRdV in this theorem is dRdx cross dRdy, and if you compute dRdx cross dRdy, it just comes out to be this. You just put it into the determinant. It's minus dz dxi minus dz dyj plus k. You can do that for fun homework if you get interested in proofs. I won't ask you to prove it on the test. But there is this dRdu cross dRdV when x is u and y is v, and you have upward oriented normal. So for n upward, you get this one. If you want to orient the surface with the unit normals or with the normals downward, having negative z component, then you just take plus, plus, and minus. And so it depends on the way you orient the surface. But this is the flux coming up through the surface then. And now we can do some problems with it. Now for page 2. Let's see. Suppose F is this velocity field, xi plus yj plus 2zk. Right? And the surface is z equals 1 minus x squared minus y squared. What's that? Well, z equals x squared plus y squared is the circular paraboloid up. If you put the minuses, it's turned upside down. Take 1 minus that, it's upside down and up a unit. We did this one earlier in the semester. So it looks like that, upside down circular paraboloid. It intersects the xy plane at what? Well, you said z equals 0, and then you get 0 equals 1 minus x squared minus y squared. X squared plus y squared equals 0. It's the unit circle is the intersection down here. So this is the region of projection is the unit circle. And what we have to do, since this is now your UV space in the first theorem, we're going to use by theorem 2, when z is a function of x and y like this, we can say that the flux is the double integral of f dot, this vector, dz dx minus dz dxi minus dz dyj plus k. You just have to memorize this, otherwise you have to prove the theorem every time. So f is this vector, x, y, 2z, dz dx, looking in here, dz dx is minus 2x, and so you take minus dz dx is plus 2x, dz dy is minus 2y, so minus dz dy is plus 2y, and then plus 1 times k leaves you 1 here. You have to double integral according to theorem 2, f dot this normal vector, 2x, 2y, 1, dA. Well, the dot product is x times 2x is 2x squared, y times 2y is 2y squared, 2z times 1 is 2z. And now, in order to integrate over the region, this dA is dx dy, you have to replace z in favor of what it is in terms of x and y. So this theorem, you could put f of xy, z of xy is really what you're putting in here. What, z gets replaced with 1 minus x squared minus y squared since it's a dependent variable, and we have this integral. Oh look, the 2x squared cancels the minus 2x squared, the 2y squared cancels the minus 2y squared, only in a book problem, right? Now we're left with the integral of 2, we pull the 2 out, we just have integral twice, double integral dA over this region. Well wait, the region is the unit circle, I know its area, right? The area of a circle is pi r squared, pi times 1 squared. We just have that the flux here is 2 pi for this surface. That's the amount of fluid per unit time flowing through the upside down piece of paraboloid. Now finally, that was illustrating the use of the corollary. What if we have a surface that's given parametrically, not z as a function of x and y, but a function, the vector value function is a function of u and v. Here's x in terms of u and v, here's y in terms of u and v, and here's z in terms of u and v. If we give this parametrically given surface, which is actually part of a cone, and suppose we take the part that u goes between 0 and sine v, and v goes between 0 and pi. And so this sweeps out a surface in x, y, z space as a function of u and v. Now we have to use the original theorem. Go backwards, I put this harder one for last, right? You double integrate over the uv space, this region. F dot dr du cross dr dv dA. That was the first theorem, equation 1. And now f is, well, if f is root x squared plus y squared k, then it's 0, 0 root x squared plus y squared. dr du, well, just take partial with respect to u and you get cosine v, sine v, let's see, 2, yeah, so, and here it is. And dr dv, take partial with respect to v, you get minus u sine v, minus u, plus u cosine v, and partial with respect to v here is 0. And you take dr du cross dr dv, it's ijk, dr du, dr dv, and the cross product then is I times this minus this times this is I times minus 2u cosine v, minus j times, and you wipe out each row and column, this times this minus this times this is plus 2u sine v, and so minus and minus becomes, let's see, I guess that's a plus there. It doesn't matter, it falls out. Let's see. Yeah, that's a, let's fix it. That's a minus and that's a plus. All right. And now when we dot product those, we get 0 plus u times square root x squared plus y squared is now the integrand. Integrated over the region in uv space, v went from 0 to pi, and within that u went from 0 to sine v. But we have to replace x squared plus y squared in terms of what they are. Well, this is x, u cosine v, this is y, u sine v in the parametric representation. So we have u squared cosine squared plus u squared sine squared. Square root is, replaces this. And so now cosine squared plus sine squared is 1. Square root of u squared is u, when u is not negative like this. So we have u times u. We have to double integrate u squared over this region. Well, this is the this is u cubed over 3 evaluated from 0 to sine v gives you 1/3 sine cubed. We can evaluate that integral, that's not too hard. You can substitute, write this as 1 minus cosine squared times sine and substitute u equal cosine. U substitution does this, and you wind up with 4/9. There's the last integral. Try doing some of these out of the textbook, and there's just 2 formulas to memorize basically to do flux integrals.